Hey everyone, today I want to talk about system calls or syscalls on Linux. I'll be on x86-64 for this example, but it doesn't really matter what architecture you're on, so long as you're running the examples on the same architecture. Now, if you're writing programs in Go or Rust or C or Python, well, at some point you're going to need to make a privileged operation that you're not allowed to do. And to do that privileged operation, you need to do what's called a system call or syscall, where you call out to the kernel and you say, hey kernel, can you please do this privilege operation on my behalf and give me the result back? And what are these privilege operations? Well, usually it's reading or writing a file or doing some network IO. And your program can't do that by default, so it uses system calls. Now, regardless of which program language you use, ultimately they're all using the same system calls under the hood. If you don't believe me, let me show you. Here are 4 invocations of 4 different binaries. The top left has a C binary, and the other ones have Go binaries, which are using different packages under the hood. But if you look closely at this output, they're all using the same system calls, and they're doing the same thing. Open, read, write, close. Let's talk about this. This is what this video is going to be about. We'll go through these 4 different examples, compare and contrast them, and see what's actually going on under the hood. Let's start with C, because C is usually as close to the metal as you can get without really writing assembly. So here I have just one main.c file, and if I look at that and open it up, I'm not really doing anything complex here. I'm including a couple header files, I'm opening a file, writing some data to it, seeking back to the beginning, reading the entire file's worth of data, and then closing the file. So pretty standard operations here. And if I compile this program, and then I can actually run it, you'll see that I opened a file, and the file descriptor that I got back was number 3. And this kind of makes sense, right? Because 0 is going to be standard in, 1 is going to be standard out, and 2 is going to be standard error. So the next logical file descriptor would be number 3. And then I wrote 17 bytes to that file, read them back, closed the file. Very simple program here. Let's run this with strace, and we'll look for specific system calls to be called. And the system calls we're going to look at are open at, read, write, and close. So when I run that, you see that my program looks to start right about here, where I open this text.txt, I write some text to the standard out, right? Standard out is file descriptor 1. I write some text to the file, I read some text from the file, and I close the file. So this is kind of where my program is. But you'll notice more system calls occurred before my program even ran. So like, what are these things? So you see up top here, you have this open at to open up the ld.so.cache and the libc.so.6. What's going on here? Well, C doesn't have a runtime, right? But the program that I wrote requires functionality from the libc library. And you see that here. This is a dynamically dynamically linked program. So it needs to get those function calls, the opens, the whatever, from the libc library. So it needs to find that. But in order to find the library, the linker itself needs to know where the libraries are and what do we even have. So the very first thing that this C program does before it can execute the code that I've written is it needs to load a list of the libraries and where they are, open the library that we need for all the calls that we need from the headers, and then it can run all my stuff. This is pretty cool. This is like as close to the metal as you can get without handwriting assembly to make your system calls. Pretty neat. Let's see how this compares to other files or other programs in Go. Let's take a look at the Go code first. So I have a couple different Go examples here. I have one using the OS package, which is like our high level example. I have one using the Syscall package, which is going to be our mid example. And I have one using raw system calls, which is going to be our low level example. So let's look at the OS file. The program here is using the standard library features that any Go programmer would use to open, read, write, and close a file. You have os.openFile, file.write, file seek, file read, and file close. And this is a normal program you would write when you're going to interact with a file. So if we compile this program, you can see that it's compiled. We'll run it, and you can see it opened the file, wrote the bytes, read the bytes, closed it. Notice how we don't get the file descriptor number here because at this high level, you don't really care about file descriptors. You really care about the file name or the path. So that's what you're getting at this higher level API. What if we strace this? If we trace this, you'll see that our program starts way down here. This is where it opens the test.txt, writes some data, reads some data, closes the file. You'll notice that this is many more syscalls than the C version. But why? So let's take a step back. The first thing you'll kind of notice is one difference is the C version used file descriptor number 3 for the test.txt file, but this Go version is using file descriptor number 4. Why? Well, there's a bunch of stuff that happened way up here before the Go code that we wrote in our file even ran. This is the Go runtime doing its thing. Now Go, unlike C, has a runtime, right? So these system calls that are running here, this is the runtime getting started and setting itself up. And it's doing its sort of like system checking to prepare itself to run your Go program. Now, to be completely honest, I don't know what all of these things really are under the hood, but I'm guessing that these sort of C group versions, or at least the transparent huge page is just reading a setting, it looks like. Same thing with this mount info. And the C group stuff is just setting up, it's reading its C group information to control things like the number of threads that it can use, or really the number of Go routines it can spawn for the runtime. But you'll notice that all of these got file descriptor 3 because they opened the file, got file descriptor number 3, did something with the file, and then closed it. But the last one, this one right here, never closed the file. So it claimed file descriptor number 3. So by the time my program was able to run, the only next available file descriptor was file descriptor number 4. Here you can clearly see the overhead of Go's runtime, which is kind of cool, right? But otherwise, this program is pretty identical to the C version in terms of system calls. Let's look at the next example. So again, I still have those 3 Go examples. Let's drop down to the mid-tier example, or the Syscall version. So if I look at the Syscall version of this file, I'm no longer using the OS package, now I'm using the Syscall package. And the Syscall package has a lower level API than the OS package, but still a higher level API than doing raw syscalls directly. So you see here that I'm calling syscall open to open the file. I am then going to write data into that file. And notice how we're working with file descriptors again, rather than file names. Then I'll seek to the beginning of the file, read the file, and close it. If I compile this, and then I run it, this one's syscall, you'll see open file with file descriptor 4, because I don't have the name of the file. I don't even care about the name of the file because I'm using the syscall package. Now I'm back to that file descriptor way of working rather than with a file name. Otherwise, everything's the same. Writing 17 bytes, reading 17 bytes, closing the file. What if we trace this? Well, really, what did we really expect, right? This is basically the same exact code as the high-level API that we've seen, but we're just using a different standard library package. We're using the syscall package. So you still have the program running way down here, and it's doing the same thing, right? It's doing its opens, its writes, its reads, its closes, and the runtime still has to set up. And there's really no difference here, right? You still see the same Go runtime doing the same setup, claiming that same file descriptor 3 for whatever it's using this file for, and then now our program, the only file it can have access to, or the next available one, is file descriptor 4. And otherwise, this is the same functionality. But look at the code again. This is kind of miserable to work with, right? You have to carry this file descriptor all throughout your program. You don't get like nice methods like the OS package gave you, right? Because before we did a OS open, we got a file object back. That file object had methods on it to do reads and writes and syncs. And like, this is all just syscall stuff, and you kind of have to pass this file descriptor around. It's a little more unergonomic, unintuitive, but otherwise, it's the same program. Let's drop a level now and look at more raw syscalls. Now, let's drop to the lowest level here. Not really the lowest level, but the lowest level that we have. And let's look at these raw syscalls. So I do have the same examples. I will show you the code. So this is now using the lowest level that we can kind of go without being kind of wonky in the program. But already you notice this is much more verbose. Now, I don't even have the syscall sort of helper package anymore. I now have to know that I'm targeting Linux x86-64 And I need to know which syscall numbers are even there. And this is needed because the way a syscall works is you need to tell the processor on your specific platform and architecture which syscall you want to execute. And on each architecture and platform, they have a specific number. And you need to know these numbers. And I'll show you that in a bit. But knowing that we know the numbers, we can now make syscalls directly using this generic syscall wrapper that takes a bunch of like pointers, really, like a bunch of raw pointers. So here I can say I want to perform the open at syscall, and I want to use the, that FD CWD from before, give it the file name as a pointer, give it the read write, yada, yada, yada. Much, much more verbose than either the syscall mid-tier level or the high-level OS package. This is frustrating. And look, we didn't even get through the whole file yet, and we're only stuck on the open. Going down, you'll see we're doing another syscall for the writes, then another syscall for the seeks, and then another syscall for the read, and then another syscall for the close. Much, much more verbose, and something that you're probably not going to write in your average Go program, but it's available to you if you want to do it. Again, let's compile this. Let's run it. So we'll do raw, same sort of output, file descriptor, wrote bytes, read bytes, closed file. And then if we strace this, same idea. You'll see our program starts down here. Same file descriptor number 4, opens test, writes bytes, reads bytes, closes the file, and that same runtime overhead. So again, this code at this lowest level of Go is the same as the mid-tier level is the same as the high-level OS package. The same system calls are being called here. And yes, I am filtering for specific system calls, so I'm sure there's other system calls that we're just completely ignoring. But for the sake of this video, these 3 programs in Go are exactly the same, which is really, really nice. But let's be honest, you're not going to want to write this raw syscalls way in Go. It's pretty gnarly. It's very verbose. We're going to avoid it. We're going to use the OS package and the syscall package if necessary. Let's see all 4 of these again in comparison. Jumping back up to the split screen window I had earlier, you can see all 4 programs again. The C program is in the top left. The Go program with the OS package is in the top right. The Go program with the syscall package is in the bottom left. And the Go program with raw syscalls is in the bottom right. And you'll notice they all look the same. If you can find where the program starts on each of these, you'll notice that all of these do the exact same thing. And that's actually pretty neat. So the point of this video and the reason why I want to kind of show you and give you some sort of kind of inspiration and pique your interest a little bit. Because look at this. You have 4 different programs, 4 different sort of levels of abstraction across 2 different languages, and you get identical system calls on Linux x86 64. That's the beauty of programming. That's the beauty of this field. We have these abstractions that we've been building to do the work that we need to do, and really under the hood, they work kind of the same. And I really love that. Now, the last thing I kind of want to talk to you about is where do you find out the syscall numbers for your operating system? Well, you can use a program called AU Syscall, which is actually a pretty funny name. I don't actually know what the AU stands for, but it sounds like I'm saying AU, you over there. And if you dump all of the syscalls out in their numbers, I'm going to grep for the ones I care about. You can see here's those numbers for my Linux x86 64 platform. And you can see oh yeah, OpenAT really was syscall number 257, and read and write and close were 0, 1, and 3 respectively. And this is the power of Unix, really. No matter how high level you're writing, eventually everything has to kind of come down to the kernel layer and work with the kernel through the syscalls. And all these abstractions that we're making are really just convenience. But under the hood, everything's kind of the same. So yeah, now you know what your programs are really doing. And I have a few things for you at the end of this video that I wanted to give you, kind of some promotion, some help for my viewers. Let's dive into that. Okay, so here's that treat at the end that I want to give my viewers and listeners and whoever is watching this. Now, to date, I have not done any sponsorship for this channel. Nobody's paid me to make content. I generally don't like people to pay me to make content. If you want to send me things to like look at and review, that's fine. But I don't want to take your money to put paid content out there because that provides an incentive, usually a negative incentive for me to make content that's not really applicable to my viewers and really not even interesting to me. However, I do have some things for you that I want to share with you. And again, not sponsored, but I want to show you. I read from cover to cover this Linux programming interface book. It's massive. Look at this thing. It's like what, 1,500 pages or whatever? Yeah, this thing, 1,300, 1,400 pages. I read this thing from cover to cover. I didn't really know all of what this is talking about. I still don't, right? I'm not a systems programmer by day. I'm more of an upstack programmer, right? At that API sort of level. But this book was fantastic. And now No Starch Press has released a kind of a new book that is building on the content in here. And if you're wondering what's in here, this is all about system calls in Linux. Basically, every chapter goes through the various system calls in Linux and how they're used to do threading, multi-threading, to do process management, to do whatever. Very cool read. Probably recommend reading it as jump to the chapter you care about and go from there. But this is not what I have for you. What I have for you is No Starch reached out and sent me a free copy of this system programming in Linux book, which is really cool as well. Now, I haven't personally finished this because they sent it to me maybe like a week or two ago, and I haven't gotten around to reading the whole thing, but I did read the first couple chapters, and there's some good content in here, and it builds on top of sort of that system call stuff from the previous book. And I say previous book, but they're not like a series or anything, but it builds on top of the content from the previous book, but more hands-on and like practical. It doesn't go Syscall by Syscall. It kind of goes, feature by feature. Let me show you. Now, in here, there's the book. Here's the detailed kind of pages, right? The content. Look at what's in chapter 2. System calls. There's a whole section about system calls, and it shows you like how these sort of things work and the fundamentals of system programming. This is what I want to share with you. They not only sent me the book, a free copy of the book, they also gave me a coupon code to get a percentage off of the book. Now, I forget the percentage off. I think it's 25%, but you can find out if you use it. But the code is System Linux 25. I'll put it in the description in the video, or maybe on the screen if I do some editing and know how to actually do editing right. But the whole point of this is I want to share this sort of benefits with you, the viewer. And here's the book title. Here's the book content. Use that System Linux 25 code. I think it expires December 12th of 2025. So go ahead and use that. But this is not, I don't get any kickback from that, by the way. This is just to share with you. Reason why I'm sharing this with you, though, is I love learning and I want to help you all learn. And if I can do my part in helping you get a cheaper book or whatever, that's a good thing. But these things, the content that's in these books is so interesting, and it helps you really understand the various layers of the stack and just kind of well-round you and solidify you as an engineer. So take advantage of it, have fun. It kind of prompted me and inspired me to make this video because I was like, yeah, I remember learning Syscalls and I remember being confused about them. So hopefully this short little video like inspires you in the same way and just interests you and say, hey, whoa, these are the cool things that happen under the hood. Okay, I want to do more of that stuff. I want to learn more about that stuff. Well, here's your opportunity to at a cheaper cost. And the second thing I want to show you is my wife's chocolate shop. So again, we own this shop. She's a chocolatier. This is me just kind of showing you all, hey, if you use that same coupon code, System Linux 25, you'll also get a percentage off at our chocolate shop to send chocolates for the holidays to whoever you want. So go ahead. My wife does a lot of hard work here. I love to promote this when I can. But if you're in the need of chocolate, specifically chocolate bonbons as little gifts, go to lilyandsparrow.net and use that same System Linux 25 coupon code. I think I'll make that expire a week after. So what is that, December 19th, 2025? So yeah, go ahead and do that. But this is me kind of shilling a little bit, but I'm allowed to shill. It's my channel. No, but seriously, thank you all for being here, for watching. I really hope you enjoyed this video. Let me know if you did or didn't. Thumbs up, thumbs down, subscribe or not. I don't rely on this channel to like be my primary source of income, but it would be nice to get some income from it just because it really helps make the videos and go. Because it's hard to like, time is tough, right? Being busy at work, being busy with the chocolate shop, just time is tough in general. So if I do want to make more of these videos, but I can't just say no to other things to do that. So I'm trying to figure that out without being one of those cringy viral YouTubers that's making content just to game the system and get money. I really still want to help you all. So yeah, I'll see you around and let me know if you like this or not. Bye.